Welcome to EduLinkUp. This is the easiest find the duplicate number tutorial you'll find anywhere. We will solve this two ways. First with a frequency array in O of n time and O of n space, then with Floyd's tortoise and hare algorithm in big O of n time and big O of 1 space. The problem states that given an array of n+1 integers where every value is between 1 and n, exactly one number is repeated. Find it. Our first example is 31342. The simplest approach, use a frequency array. Create an array frequency of size n, all zeros. Scan through the input. For each element, check its slot in frequency. If it's 0, mark it. If it's already marked, you found your duplicate. Array is 31342. Frequency starts as 00000. Index equals 0, value 3. Frequency of 3 is 0, mark it. Frequency 00010. Index 1, value 1. Frequency of 1 is 0, mark it. Frequency is now 01010. Index 2, value 3. Frequency of 3 is already 1, not 0. Duplicate found. Return 3. That's it. One pass through the array, one lookup per element. Big O of n time, big O of n space for the frequency array. Now the code. Method find duplicate takes the int array nums. We get the length L, create int frequency of size L, all 0 by default in Java. We loop through every element. If frequency of nums of I is 0, we mark it as 1. If it's not 0, we've seen this value before, return nums of I. If the loop completes with no return, we return 0, but the problem guarantees a duplicate exists, so the line never actually runs. Clean and simple, but it uses big O of n extra space. Can we do better? Yes, we can do better with Floyd's cycle detection algorithm, also known as the tortoise and hare algorithm. So our second example is the array 13422, where the duplicate is 2. The challenge here is that we cannot modify the array and we cannot use extra space like a hash set. We must solve it in big O of n time and big O of 1 space. The key insight is to treat the array like a linked list. The array is the current node and the value at that index is the next pointer. So array of index tells you which index to visit next. Because there is a duplicate value, two different indices will point to the same next index. This creates a cycle. Notice that the cycle is formed at index 2. Floyd's strategy has two phases. Phase 1 detects if a cycle exists. The slow pointer moves one step at a time using array of slow and the fast pointer moves 2 steps. Phase 2 finds the cycle entrance, which is the duplicate. We reset the slow pointer to the start and keep the fast at the meeting point. Let's trace phase 1. Both the pointers start at index 0. In the first iteration, slow moves to index 1, fast jumps to index 3. In the second iteration, slow moves to index 3, fast jumps to index 4. In the third iteration, slow moves to index 2, fast jumps back to index 4. And in the fourth iteration, slow moves to index 4 and fast loops back to the index 4. The meeting point is found at index 4 and a cycle is detected. In phase 2, we find the cycle entrance. We reset the slow pointer back to the start at index 0 and keep the fast pointer at the meeting point 4. Now, both move one step at a time until they meet again. Let's trace phase 2. Step 1, slow moves to index 1, fast moves to index 2. Step 2, slow moves to index 3, fast moves to index 4. Step 3, slow moves to index 2, fast moves to index 2. They meet at index 2, that is our duplicate value. Why does this work? The math behind Floyd's guarantees that the distance from the start to the cycle entrance equals the distance from the meeting point to the cycle entrance. So, when both pointers move one step at a time from their representative reset positions, they collide exactly at the entrance, which is the duplicate value. Now the code for this. Slow and fast both start at nums of 0. The do-while loop runs slow equals nums of slow, fast equals nums of fast until they are equal. That is phase 1. Phase 2, Reset fast to nums of 0. Now a regular while loop, slow equals nums of slow, fast equals nums of fast until they meet. Return slow, that's the duplicate. Notice it's the fast that resets to nums of 0, not slow. Slow stays at the phase 1 meeting point. That's the key to phase 2 working correctly. Big O of n time, the pointers traverse at most the length of the cycle plus some constant overhead. Big O of 1 space, just 2 integer pointers, no extra arrays. Thanks for watching. Subscribe to EduLinkUp for more data structures and algorithm breakdowns. Master the algorithm, master the code. See you in the next one.